here, we would think it's too crowded, but it's nothing compared to India. And India has really good food, but I'm not sure it's the American digestive system is prepared for that level of, you can't have biryani that many days in a row and expect to survive. Is that is kind of the punchline. What's this? Oh, it's good food though. Yeah, and we have some places or near here that have very good, like authentic Indian food, but we're just not prepared to eat that every day. It's a treat, like a once every couple of weeks type.
You don't eat sushi every day. You will get sushi.
Yeah. Okie dokie. What are we doing here? All right, so let's see what class is this? All right, so last class we were talking about, we started talking about pointers, right? Yep, so we talked about pointers being a primitive type variable that knows how to hold memory addresses. And I've mentioned that pointers are intimidating to, really all computer programmers. You will run into, I would probably say 70% of even professional software developers get intimidated by memory. So my goal here is and part of that is that I think that they didn't really learn about how memory works early on in their computer science career, because some of our newer languages tend to hide some of this stuff from us. But that doesn't mean that that the consequences of it aren't still in play, and we're gonna see that here. But last time we looked at, we printed out some memory addresses and we saw, the crazy looking hexadecimal looking things. And we looked at a special syntax for these guys. So we have a pointer syntax in C++. So we have an asterisk. Asterisk says, get me the value that lives at a memory address. The ampersand says, tell me the address where something lives. Okay. And we can use this on both sides. We can set the value at a place, or we can get the value from a place. And we'll see that through some examples here as we go through here. All right. So now we looked at some examples where I think I created some integers, and then I created an integer pointer that held the memory address of an integer. And we just kind of looked at some examples of that, like what looks like an address, what doesn't. But really typically if we are writing software, if we're working with integers and things like that, we're probably not really messing with pointers. More than likely. There are situations where maybe you want to pass an integer into a function, make a change to it, and then have that change felt globally. But that more than likely is more of like a forced example, like something you might do in like a class like this where we're trying to like show a point. Practically, that's something you wouldn't necessarily do in industry. Typically, if we are dealing with integers are tiny little things, right? So it doesn't really benefit us to hand somebody the address where an integer is, as opposed to just the integer itself, right? If this thing's been sitting here for a month, but if I have this thing, I could throw this at one of you, and this is small enough that that's not a ridiculous thing to do, right? So I might pass this to you by value, right? Because we talked about pass by address versus pass by value. I might pass this to you by value. Now in the computer world, what would actually happen is I duplicate this with my black magic, right? So poof, duplicate it, throw him the copy. Now anything he does with that is not going to impact the original. That's passed by value. And the thing is, this is light enough where that's a reasonable thing to do. Where again, I want to connect back how we problem solve with computers to how we problem solve as human beings, right? If I'm going to give you a quarter, I'll toss you the actual quarter. I won't write down a little post-it note where you can find the quarter on the ground somewhere. But if we look at something like houses, it would never be reasonable for, let's say I'm having a party at my house tonight. I wouldn't say, here's my house, open the door at 8, right? Because houses are heavy, they're big. So we would say, why do you give somebody your address? Because it's a lot lighter. It's convenient to tell somebody where they can find your house as opposed to handing them the house. Make sense? That's why we might want to use addresses to do things. And a language like C and C++, it empowers the programmer to decide how we want to handle this. Newer languages like Java and C# make those decisions for us. For instance, is it reasonable to say, using my party example, is it reasonable to say that it would never be reasonable for me to hand you the house? That would always be an unreasonable thing to do. You know, an awesome feat of strength, right? Okay. But it would never be reasonable to do that in real life.
Or it could be a dollhouse.
Could be a dollhouse. Okay. That's true. But generally speaking, right, it would never be a reasonable thing to do. So it would be reasonable for a programming language, a newer language, to say, look, I'm going to not make you have to deal with extra decision making, extra syntax. Because if you're going to give somebody a house, you're going to give them an object. We're going to start talking about objects here fairly soon. If you're going to give somebody an object, we're just going to go ahead and give that as an address by default. It'll be passed by address by default. In C and C++, the programmer gets to choose. We are empowered to choose. We should 99% of the time choose reasonably, right? But we could pass somebody the entire house if we wanted to. And there might be some outlier type of examples where maybe that makes some sense in a certain problem you're trying to solve or whatever. All right. But realistically speaking, when we're dealing with computers, we're not really talking about the weight of something. We're talking about the size of it in memory, right? So if we translate this idea of a house, you know, in real life, a house is really heavy. We can't lift it. In a computer, a house would just take up a whole bunch of memory, and we'd rather tell them where they can find it in your computer's memory rather than hand them this giant chunk of memory. Make some sense? Okay. But when we're dealing with C and C++, as a programmer, we're empowered to make these decisions, even though we should probably make the same decision all the time. Depending on the kind of animals we're dealing with. But I like the language from this perspective because it forces us to learn about memory, which is going to then put you in that 30% of people as professional developers who actually aren't running and hiding under their desk as soon as pointers get involved. And I'm not exaggerating. It really is something that people freak out about just because it's intimidating. You know, you wonder like, hey, why do we spend this time doing conversions between hexadecimal and stuff? Like, well, what am I going to run into that in real life? Well, not very often, but every now and then you might. But every single time you see a memory address, that's a hexadecimal value, and it's going to freak you out. Even if you've done things that are conversions between stuff, we like to stay with, 10 fingers, 10 toes. Let's stick with decimal. Makes some sense to us. All right, so we started talking about this kind of animal called an array. All right, and I showed you a starting point for an array, and what I mentioned on Slack on Thursday, and then sorry I had to cancel class at the last minute there, is that what I want to look at today is the difference. And I think you had brought up last class, like, oh, why wouldn't you just write it a certain way? And we're gonna look at that today, examine that today. But we're gonna look at the difference between the ways we can create arrays and the consequence of doing it one way versus another. And similar to what I said about curly braces, like always use them. It's never wrong with like a for loop or an if statement or something like that. If you always create arrays in the way that I'm going to suggest you create them, it'll never be wrong. But if you create them in the way that's allowed, sometimes it's going to have a consequence that maybe you weren't expecting, something like that. And we'll look at that today. All right. But bottom line is, if we create an array like this, int AR5, and let me just throw this back into code here. Where do we leave stuff? Yeah, I'll just throw it in the main. So if I say int AR5, I'm creating an array, a single variable named AR that holds, well, that is capable of holding 5 integers. So it's kind of like getting one of those little shoe organizers, right? So it's got 5 little buckets where I can throw an int into each of the buckets. And that guy will look something like this. Right now, it doesn't have any values in it as I've written it currently. Okay. And it's 0 index, just like strings. So if there's 5 elements, it's bucket 0 to 4. But these guys live at a memory address. And just to kind of show that real quick, and we've done this before, but just as a reminder, if I print out AR here, we see we get freaky deaky memory address. All right. And what this address is, what we're looking at right there, is the equivalent in my picture to the number 100. It's called the base address of the array. Where does the array start? Okay, that's when you print out a value, and I'll come to you in a second. When we define an array and then we just print out the value of that variable, it's giving you where that array begins in memory. And the reason why that's important is arrays require something called contiguous memory. That is memory in a row, memory right next to each other. So if I'm going to hold 5 integers, I'm asking the operating system to go find me a plot of land big enough to hold 5 integers right next to each other. And the size of an integer is 4 bytes, 32 bits. I'm asking it, find me 20 bytes of land, 5 times 4. Find me 20 bytes of land right next to each other. And then we're going to store inside of that variable AR the entrance to that land. And then if I need to get bucket 0 of that guy, the first element, it lives right there. If I want to get bucket 1, I take 1 integer size step. And now I'm at bucket 1. If I want to get bucket 4, I'll take 4 integer size steps. And now I'm at bucket 4. So as long as I know where that array started, I can calculate where a certain bucket is by doing multiplication based on the size of that data type, in this case, an int. But that only works if all that memory is right next to each other. Good.
That has one memory address, or like, so does each number have its own memory address?
Yeah. So like in this example, here's my 5 buckets. This guy in my simplified example here, it started at memory address 100. So the value of AR here equals 100, which also happens to be the address of bucket 0. Bucket 1 has its own memory address. Bucket 2 has its own memory address, so on and so forth. But notice these guys do live right next to each other. When we constructed that array here, the consequence of this syntax says, give me 20 bytes of memory right next to each other. Each bucket will have its own address, but we only actually need to know where it begins. If I want to get to bucket 2, I'll start at, so here I have my example here of bucket 3. I'll start at the base address, which is 100. I'll add to that 3 times however big an int is. And an int is 4 bytes big. 3 times 4 is 12. 100 plus 12 is 112. And that's bucket 3. So you can calculate the location of it because each bucket does have its own memory address, but all we actually remember inside of our variable is where that plot of land began. And then we can take hops from there.
So when you did CL, did that with AR.
That memory address is the value that's actually stored inside of AR, which is the same memory address as the very first one, bucket 0, the beginning. So if you do this, if you do the same thing here, if I say I want AR at bucket 0, that's going to be whatever value AR holds plus 0 times size of int, and 0 times anything is 0, right? So that's going to be memory address 100 plus 0, which is 100. That's where bucket 0 is. So the value of AR is the same as the location of bucket 0. Those are the beginning, the entry point into the array.
So arrays are memory.
Arrays are plots of land in memory where they are dictated by how much data do we need to store. We're actually going to be talking about the size of it today. So if that's a little fuzzy, that's okay, because we're going to be exploring that more today. But for right now, what we want to think about is I could create a single variable name capable of holding multiple same kind of values, like multiple integers. And how does the language manage that? It asks the operating system for a bunch of land to hold that stuff. But very importantly, that land is right next to each other. It has to be in contiguous memory. Otherwise, this little trick of getting to bucket 3 doesn't work. We can't just go to the beginning and then hop 3 times to get to bucket 3 unless we know that all that memory lives right next door. Yeah, it's dictated by that number. So the amount of land we're getting is dictated by this number right here. Like in this case, I have a 5 times however big that dude is, an int in this case. If I had a char there, chars are 1 byte in C++, so I would only get 5 bytes of memory to hold 5 chars. But to hold 5 ints, I need 20 bytes of memory because an int is 4 bytes or 32 bits. Make sense? Yeah. So we're just asking the operating system for a plot of land big enough for holding something. But the punchline to that is the memory itself memory is memory. Just because I've advertised I'm storing integers here, that dictates how much memory we ask the operating system for. I could put chars there if I want. It's just not going to walk it correctly because I've advertised this guy as being a collection of ints. So if I want to get bucket 3 and I expect there to be a char at bucket 3, well, I'm only going to take 3 byte jumps in there. And where am I going to end up? I'm going to end up 3/4 of the way through the first integer. I'm going to pick up whatever bytes or whatever bits I find there. So it's going to start at, let's say bit 24 and then read from there 4 bytes in, 32 bits in from there and say, okay, what number is that? All right, makes some sense. Memory is memory. There's not a special kind of memory for chars or special kind of memory for ints. Memory is memory. The type just dictates how big of hops do we take when we need to move from value 0 to the value of bucket 1 to the value of bucket 2 and so on and so forth. All right, other questions about this? Go ahead. Yeah, right. So when I said 3 here, that's base address plus, I need to take 3 steps. How big is that step? It's however big an int is. If my type here was a char, this would be size of char, which would come out to be a 1. Yeah. So this just tells me, which is the next step of land I'm going to hop into. How big of a step do I take, right? To get to the right place in memory. A language like C and C++ allows us to play some weird, funky tricks where I could choose to take a char size step through memory and end up starting in the middle of an integer. Well, since an integer is just made up of a bunch of zeros and ones, if I start off in the middle of an integer, I'm going to get, let's say the second half of one integer and the first half of the next integer, which is going to be some unpredictable random value, right? Which was just made up of those 32 zeros and ones put together, starting at the funky place that I just randomly decided to start at because I took a 1 byte step instead of a 4 byte step. Make sense? So hopefully that's kind of depicting why people get scared of memory. It's not really a difficult concept under the hood, but as soon as we move outside of our comfort zone, it becomes an intimidating type thing. I keep trying to drag it back to a real life situation where if you had land in front of you and you had I don't know, some paving stones or something like that, and those stones were 4-foot long stones, you would have to take longer strides to step from the first stone to the second stone to the third stone, as opposed to having maybe little bricks that are char size, right? And if I needed to walk from one brick to another brick, I would take little tiny steps to go from those same 5 bricks. Okay. All right. Any other questions about this, at least at the baseline? We're going to be exploring this a lot more today. All right. So let's do a couple of things here, and then this is going to roll us into our need for objects, because we're going to see a limitation today. All right, so we already know that I can define a array like this, and I think I may have shown you the other way of doing it, or at least I put it in Slack, but we'll talk about that from a starting point today. But let's just start with the weakness of this right now. So what I'm going to do here is I'm going to say void. I'm just going to create a function. Let's call this guy create array. And what create array, I'm going to actually create a couple. Well, let's just write this one first, and then we'll write the other ones. So what create array is going to do is we're just going to create an array of values. So int AR5, something like that. All right. Nothing interesting there. If I say cout AR and L, we're still going to get a memory address. So then up here, instead of defining it here, I'll just call my create array. And I've just relocated that code inside of a function, and I called the function. Okay. All right. But it is important in our example here that I am creating this inside of a function. All right. So now I want to do is I want to go ahead and I want to write. I'm going to go ahead and fill this guy up. And I'm going to go ahead for our example right now. I'm going to just hard code in the size of the array because I know how big I created it. In a little bit, we're going to talk about one of the problems with arrays in C and C++ is they don't know how big they are. All right. And we'll explore that a little bit. But for right now, for the starting point of this, I know I built it to be size 5, so I'm just going to make that assumption. All right, and I'm going to go ahead and just fill up AR. So I'll put at bucket 0 a 0, at bucket 1 I'll put a 1, at bucket 2 I'll put a 2. I'm just filling it up with some numbers. Okay. Up to 4. It'll be 0 to 4 for 5 total numbers. All right, so now, and here I'll go ahead and do. I don't think this should come as a surprise, but I'll do it anyways. We're going to see that the value in AR has not changed. AR is the base address of that array, regardless of what I filled it up with. So we're going to see the same memory address twice here. Okay, same memory address. I asked the operating system for some memory big enough to hold 5 ints. It gave me the address where that memory was. I then use that memory to go ahead and fill it up with some numbers 0 through 4. But then I proved that, hey, the base address didn't change. All I've done is I bought a plot of land and then I happen to have built a house on it. All right. The location of that land has not changed. There's just something there now. Okay. So what I'm going to do is I'm going to write another function just for our little experiment here called print array. And again, I'm going to assume that I know this array only has 5 elements in it. And this guy is going to take a memory address as a parameter. So it's going to take in as a parameter an integer pointer. The base address of where this array starts. And we know that we're going to be taking integer size steps through there. We'll see that here in a second. But that's what the parameter of this is going to be. The memory address of an int. That's what this variable type says, int pointer. All right. And what I'm going to do is I'm just going to go through and I'm going to print out the elements of that array. And again, I mentioned that I'm just going to, for our example, I know I have 5 elements in there, so I'm just going to assume there's 5 in there rather than show you another problem with arrays at the moment. We'll talk about this in a second. Punchline is arrays have no way of advertising their size. And for those of you who are wondering, based on our slides, can you just use the size of function? The answer is sometimes, but not always. And we'll look at that a little bit, but there's a better way. All right. So I'm going to go through the 5 elements of that array, and I'm going to go ahead and print out each element. And then I'll press enter at the end. So we'll get 0, 1, 2, 3, 4 on one line, right? So if I come into create array, and then I go ahead and say print array, and I pass it AR, print array is expecting me to pass it the address of an integer. That's what an int pointer is. It wants me to pass it as a parameter, an int pointer. The kind of animal an int pointer is a memory address. We've already seen that AR is a memory address. When we did a C out on AR, we got freaky deaky memory address, right? So I'm handing print array the address of an integer, which happens to be the starting point for an array that we can take hops through. I happen to know that this guy has 5 elements in it, just for our example. And I'm going to go through and say, print out the value found at bucket 0, the value found at bucket 1, the value found at bucket 2, so on and so forth. All right. So let's go ahead and just see our 0 through 4. So there's our 0 to 4. What did main do? All programs begin and end with main. Main called create array. What did create array do? Create array generated an array using this specific syntax, went through and filled up that array with the values 0 through 4. Then I called my print array function, passing it the address, the base address of that array. So this guy took in an address as a parameter, and I walked through that address one integer step at a time. Bucket 0, bucket 1, bucket 2, bucket 3. How did I know that was the size step I was taking? Because the type of memory address was an int pointer, not a char pointer, not a bool pointer, an int pointer. And that dictated to me what size steps I needed to take to walk through there. Go ahead.
What is CO and L just the end line?
Yeah, I kicked it. Yeah, this is just for this. Instead of having 0, 1, 2, 3, 4, I said 0, 1, 2, 3, 4, and then I pressed enter at the end. Yeah, you could have replaced this with like something like that if you wanted to do a line return that way instead of using endl. It'll be the same output. This is line feed \n is the special symbol for line feed. Endl is just the more generic version of this because it's less of a problem now, but historically, different operating systems treated line feeds differently. You used to, in older computers, especially Unix, you used to have to do a \r, \n \r. So that's a carriage return and a line feed. Anymore, \n is kind of treated as the double whammy, both of those. Endl just says it's going to work on whatever system you're on. We'll make it function the way it needs to function to end the line. All right, so we get our 0 through 4 there. Okay. Questions about that so far? Go ahead. It was a pointer before. When I printed out, when I said C out endl or C out AR here, what's the output of that line? Memory address, right? What kind of value is this variable capable of holding? An address, because its type is an int pointer. Yeah, it is. A pointer is a primitive type variable capable of holding a memory address. What kind of memory address did I create here? And again, memory is memory. Giving it meaning in terms of the kind of values I'm storing there only informs us of how big of steps we're going to take as we walk through memory. All right. So this goes back to that real life example is if I have 5 large paving stones in front of me, those are integer pointers. I'm going to have to take 5 large steps to walk through from bucket to bucket to bucket, from stone to stone to stone, as opposed to if I was dealing with char pointers, those are smaller. Those are only 25% the size of an integer in terms of the storage space it requires in memory. So I'm going to have to take little tiny baby steps as I walk through memory. But at the end of the day, a memory address is a memory address. There isn't like a special part of the computer where chars are stored, or a special part of the computer where ints are stored. Memory is memory. We've just said, hey, when you get there, this is how big of a step you should take to get to the next proposed value. Okay. So we've proven that this is a memory address because we created it right here. Then we printed it out and we got the weird hex value. We created another function that expects us to pass in a memory address, and we do. What do I do with that memory address? I reference it just like it's an array, because memory addresses are memory addresses. Go ahead. Oh, I mean, you definitely needed to put it as a parameter here because I ultimately want to print this one, right?
Well, yeah, but just like instead of having that.
Oh, have this? Oh, what kind of value is AR then? What kind of value does this variable hold? Is it? What kind of value do integers hold? A number. It's not a memory address. This guy though is a pointer. I mean, we're printing it out here. This is just a friendly syntax for creating arrays. We're proving to ourselves though that it is a memory address, as opposed to me saying int AR2 is equal to 7, whatever, 8. If I print out AR2, I'm going to get the number 8, not the memory address where 8 is. Integers know how to hold numbers. This guy is an integer pointer. I mean, I think I get where the confusion is because you see the same word here in front of them, right? The difference is that we have this special syntax over here. Let's see if it will allow me to do this. Older C and C++ did not. Java would let you do something sort of kind of like that. Yeah, it doesn't like the type. So the way you define arrays, it's this thing plus this special syntax. This special syntax right there says this is a collection of values. So this guy is going to end up being a memory address. And we proved it to ourselves by printing it out here. Okay, so we had a memory address. This guy up here is expecting a memory address. Well, right now he's expecting an int, which is going to break down real quick, because if we have that syntax on an int, it's going to scream at us and say, hey, I don't know what you mean. What do you mean? How do I go to bucket 3 of the number 8? It's not a thing. So going to bucket 3, that array syntax only works if we have an animal we're dealing with that has multiple buckets. Okay. So this guy's going to be expecting a memory address. I'm going to pass him a memory address because this guy right here creates a memory address. And when we look at what I'm going to call the preferred syntax for arrays in a little bit, it's going to be much more obvious that we're dealing with a memory address. All right. In fact, I'll just show it to you real quick. Int pointer AR is equal to the int pointer version of malloc 5 times size of int. These two things effectively mean the same thing. but they don't behave identically. And that's what we're going to look at today. But now this is much clearer that this guy is a memory address. He's a pointer. Because now I have that nice type in front of it with the int star. And this guy over here is memory allocate. That's what malloc stands for. All right. So right now you should be looking at this and saying, scary line, not so scary line. Why does he want me to do this? Probably what you should be feeling right now. But it's not that bad, other than the fact that I like human misery is kind of a hobby of mine. But where we're going is this then becomes more obvious that we are dealing with an int pointer. So this guy then matches up to this guy here, which makes us feel better. All right. And if you kind of want to see this in action, same output. All right. But I promise you there is a distinct difference between them. And we're going to explore that here in the next little bit. All right. But right now we're going to stick with that dude. All right. So we call my print array. This guy's going to print out all the values of that array. All right. So now what we're going to do is when I call create array here, I'm going to instead have create array return an int pointer. And then I'm going to catch that value that's returned there into a variable in main, int pointer AR. And then I'll call print array with that. So call create array. Create array is going to return an integer array, then pass that integer array to print array. Everything looks okay. Let me update the guy down here. Create array is now going to return an int pointer. He will no longer call print array directly. Instead, he's just going to return the array that he created. So what does create array do? He creates an array, he fills it up, and then he returns that array, returns the pointer to that array, the base address. All right. Now, if we want to just see, so if I do cout AR end L, we'll have our memory address there. We've seen that already, but we'll print it inside of create array. We'll see a memory address print. Then we'll return that guy. And what I'll do is I'll go ahead and I'll print out AR after it's returned. So we expect what prints out right here to be the same value that prints out right here. Create an array, fill it, show me the base address of that array, go ahead and return that address. That address gets caught right here inside this variable. Go ahead and print it out. We should see the same address twice. Oh, we'll look at the warning. Here's the original. This is what printed out the second time. Not the same address, right? In fact, the fact that that second one's a 0 looks highly suspicious. Probably not another memory address. That kind of looks like the default value of something, right? All right. Why do you think that happened? Let me quickly just make a little shift. Come down here and we're going to do that just to start the conversation. So I'll just change it to my other syntax. Okay. And we saw before that this is also an array, creates the memory address, blah, blah, blah. And now we're going to see that we get the same address twice. So definitely behaving differently, right? So now we have to ask the question, why? Why is it behaving differently? So let's go back to this one. So why do you think that it worked as long as we were inside of this function, but as soon as I returned that value and caught it out here, when I printed it out, it was a 0? What's your guess as to why it works this way? Go ahead. Well, did it change? Do you suspect this is a different memory address, or do you suspect that the memory's gone? Yeah, a 0 seems like we kind of have to hit the lottery seemingly multiple times in a row. In fact, memory address 0 probably is reserved memory by the operating system. Probably we're not allowed to touch it. So we really lost that memory. Any other? I'll give you a hint. It deals with scope. Go ahead. Yeah. I mean, it's probably, since we're dealing with memory, it's in the realm of that, but we're not passing anything. In this case, we're returning a value. And hey, I mean, this seems like it should work just fine. I created the memory here. I filled it up. I printed it, proving I had real memory. Hey, that guy looks like a legit memory address. Doesn't look like a mistake. Then I just returned that value. That's a memory address. No problem. Yet when I printed it, after I caught it, it became a 0. As opposed to if I use this other syntax for creating the array, now I get the same memory address twice. It works this way, doesn't work the other way. The question is why, and I'm telling you it deals with scope. And they give us a little hint here, I think. Older versions of C++, the older compilers would not have even given you a warning. So warning, this is the address of the local variable AR. Not really surprising. We look down here and we say, okay, well, here's my function create array. This creates its own scope, right? Scope is where you have access to a variable. And so this is the local variable AR. But what I'm saying is that this guy, because we requested memory using this syntax inside of this function, when this function ended, that memory was automatically given back to the operating system. It was relinquished. So even though we thought we were returning that pointer here, say, hey, here's the memory address of the thing I created. What ended up happening is as soon as this function was over, the operating system went through and erased all the memory that was associated with all the local variables that were defined inside of that function, including memory. Make some sense? No different than if I created a integer age and set it equal to 15. At the end of this function, whatever memory was created to hold that number 15 is gone. It gets cleaned up and now somebody else can use that memory because this function ended. We tried to get the value out of there. So this comes back to your suggestion, this pass by value versus pass by reference. We're not really passing, we're returning a value versus returning a reference. But if I were to return age here, we would still get the value on the outside. We'd still have the 15. Why? Because I didn't return the memory address of where they can find the 15. I handed them 15. Here's a copy of that 15. So kind of on his deathbed, his dying wish was like, here's 15. And then he immediately, it got wiped from existence. Okay, but back in Maine, we caught the 15 and we could do stuff with it, even though it's stored in a new location in memory, because Maine, it's now a local variable of Maine. But what we lost here was the address that was created in here. That address no longer pointed to a real thing because that real thing was wiped from existence when this function ended. That makes some sense? Now, if I use this other syntax here, we see that it does work. And the fact that it does work must mean that it didn't get wiped from existence. And why is that? Because we use this other syntax. Rather than, I mean, so it's easy as a programmer to say, oh, well, this is a much more friendly syntax to use for arrays. So why don't we just use that? And maybe a lot of the time you can get away with it. No big deal, right? Because maybe a lot of times you're not necessarily returning the value and that kind of stuff.
Because we're specifically allocating memory in syntax instead of just letting it disappear, we're telling it to save it.
Correct. Now, before we jump into the malloc thing, what if we just change this a little bit? What if we say this guy is going to take in an int pointer AR? So we're not going to generate it here, but we'll fill it in here. And what we'll do out here is in main, we'll go ahead and say int, call this guy my array. We'll have 5 elements. We'll go ahead and pass my array here. So we're going to pass my array into create array. Create array is now going to take in an int pointer. What did create array do? Well, he no longer actually creates it. What does he do now? He just fills it. He takes it as a parameter. He fills it up. He prints out the memory address. Then he goes ahead and he returns it. Main then catches it and we print it out again. Now we might start off by saying, oh, well, we saw that this syntax doesn't work the way we want it to work. But in this case, we're going to see that it does work. Okay, we do get the same memory address twice. Why? Go ahead. Yeah. Yes, we use the same syntax to create the memory, but this memory is owned by this function main, and main is still kicking. So that means it has not given it back to the operating system and wiped from existence. This memory right here was not born inside of this function. It was passed to this function. Oh, sorry, born inside this function. It was passed to this function, but then it was only filled in here. It was not born in there. Make sense? So when this guy died, that memory did not get erased. It was still, it did still exist in its scope, its original scope, which was in main, and that's why we have both things. So we can get it to behave the way we want it to behave. We just have to understand the consequences of when does a variable get created and when does that variable die. Make sense? So we could make a global argument and say, hey, if I always create my own memory and don't rely on the underlying behavior of the language or operating system, I just create the memory. Technically, if I'm creating memory, I should also clean it up. We can use another function called delete, and delete is like me telling the operating system, I'm now done with this memory, you can have it back. So I'm having to manually give it back, which seems beneath us, right? The computer should do that for us. More modern languages have something called automatic garbage collection, which kind of does that for us. Cleans up our own mess, a little robot that follows you around and you spill something, it wipes it up for you. All right. But as good programmers, if we create new memory, we probably should give it back when we're done using it. All right. So this comes down to this, how the scope of variables work. So this is actually nothing new. This isn't really an argument of, oh, arrays work in this weird way in something, it's a brand new way to how things that we've already been doing work. It works the same way. Any variable that you create inside of a function will die when that function ends. Any kind of variable dies when that function ends. I promise you, inside of this function right here, this variable AR, the variable here, AR, dies. We no longer have that guy. But what does AR hold? AR holds a chunk of memory that we requested from the operating system. The programmer specifically requested from the operating system. It was not requested by this function automatically and overseen by this function. This variable was. So AR disappeared. And AR's ability to hold that value disappeared. But the value persisted because we specifically allocated this memory ourselves. We took responsibility for that newborn memory and did not rely on the function to clean it up for us. Instead, we'll clean it up when we're done with it. Make sense? So we can bypass that that situation. All right. So questions on that? So I'd make the argument that you should always define arrays this way. Plus, it makes you look cool. Just look smart. It's like, you know, what are you doing there? Ah, you wouldn't understand.
Which is another way of saying, I don't know.
Go ahead.
So with the malloc, with the int right before it, is that basically the same thing as saying and in front of it?
No, and in fact, let me just test this real quick. I actually think this isn't required anymore. Well, let me tell you how it would have worked before. We'll see how this guy behaves. And this actually goes back to something you asked earlier about, you know, the int memory versus char memory or something like that. Malloc, this function malloc, what it returns is a memory address. But by default, it returns what's called a void pointer. That is a pointer to generic memory. Okay, that is, I mean, like I said before, memory is memory. Whether it's memory that holds chars or memory that holds ints, memory is memory. But we only know how big of a step we have to take if we've added, you know, maybe modernly we might call like some metadata, some extra information about that memory to tell us how big of a step do we need to take in order to walk through that memory appropriately to access the individual values. All right. So if I blindfold you and put you in front of some paving stones, using our paving stone example of the little bricks versus the big ones, and I don't tell you, I say, hey, you're at a memory address. You're at the beginning of the yard. Go ahead and walk to the third paving stone. But I don't give you any information about how big those paving stones are, but you're blindfolded. You're flipping a coin, right? You're just kind of deciding how big of a step you take. And obviously in a video game, there would be cliffs, right? Where if you miss the step, you explosions and fire and that. You know, it's rated PG, so there's no blood. It's just, you know, wah, 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 you know, at the end, something like that. Right. So that would be tough for us to do as human beings because we don't know. We know you want me to take 3 steps. You want me to get to that third paving stone, but I don't know how big of a step I have to take because you've just told me, okay, you're at the beginning of the yard. You're at the memory address where you're supposed to start, but you haven't gotten information about what kind of stuff is stored there. I still say memory is memory. 20 bytes of memory for holding 20 chars is the same thing as 20 bytes of memory for holding 5 ints. It's the same thing, but it does dictate how big of a step we have to take to walk through that memory to get to our individual values. So the default behavior of malloc stands for memory allocate. It's our way, and if you're a newer programming language, if you've worked with some newer language, malloc is the same as the new keyword. So if we were writing this, and you'll like this a little bit better. If I was writing this in Java, I would say int array AR is equal to new int array 5. That's the equivalent in Java or C#. So you're going to look at this and say, oh, well, that seems better. C++ sucks. Let's move on with life. C, this really came from C. All right. Newer languages are going to have some conveniences, and this guy will behave the same as this guy because I am specifically asking for new memory. This guy is like our real estate agent, just like in C and C++. Malloc is our real estate agent. Actually, we're going to see the new keyword relatively soon when we start dealing with objects, probably Thursday, actually. Okay. So this is our real estate agent where we're saying, hey, run out to the operating system. I need 20 bytes of land. Figure out where that's available to me and give me back the address where I can go find it. Okay. By default, it gives us a generic address, something called a void pointer. So me putting int pointer in front of it like this is me giving it context. I actually think that a modern version of the C++ compiler will not require me to do that because it will cast it to the right kind of value since I'm storing it inside of an int pointer. It'll go ahead and say, you put it into an int pointer. Whenever you use this guy, we'll go ahead and treat it like an int pointer. So I don't think that first part is actually needed anymore. I kind of like using it because I think it's explicit about, hey, I want some memory. Specifically, I want that pointer to be representative of an int pointer that tells me, that has some extra information attached about the kinds of, how big of a step do I need to take as I walk through memory. But I don't think it's actually required. Today, we'll test this here real quick. Take that dude out. Still returning it there. We're not going to pass it there. Oh, no, it does require you to do it. Yeah, see, it says invalid conversion from void pointer to an int pointer. It didn't like that I tried to take what was returned by this, which was a undefined pointer type. Again, memory is memory. There's no difference between the memory address, but we haven't given that additional information of the kind of value that we don't have the type of steps we're going to take. I would think that you could make the jump since you're putting it in an int pointer, but it screamed at us. So it does want us to say, look, treat that void pointer as an int pointer because I'm going to put in integers there. All right, makes some sense. Now, would I ever use a void pointer? We might say, well, why do void pointers even exist? What might you use a void pointer for? Okay, possibly, since we're relating it to objects here pretty soon. Go ahead.
Maybe you have some data type that's not like
Yeah, if it's not an existing data type. If it's not an existing data type, and I'm basically just saying, look, I need a place to put stuff. All right. And I'm not going to rely on it behaving a certain default way because I might put different kinds of stuff there, almost like a landfill, right? I just need a chunk of 20 bytes of memory and I'm just going to randomly put crap there. But I don't need you to make it behave a certain way as I take steps to bucket 3 or bucket 4 or something like that. It just is going to be generic memory. My guess is the default behavior for a void pointer will probably be the size of a memory address, which is probably 8 bytes. And I'm guessing they're using a 64-bit operating system under the hood here. Typically 64-bit Linux operating systems is probably what's under the hood. Either has 64-bit memory addresses or 48-bit memory addresses. So let's see, we can actually count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 of them. How big is each one of those guys? Let's see if we make some connections to stuff. How big is this 5 versus this A? This deals with our shortcut for converting between hex and binary. How many bits do we need to represent each hextet? 4. 0 through 9, A through F, that takes 4 bits, right? So if I have BAD, I can, B is the value 11, right? I can write in 4 bits the number 11. I can write in 4 bits the number 15. I can write in 4 bits the number 7. So hexadecimal can be represented in its entirety with 4 bits. Just like octal can be represented in its entirety with 3 bits. So since there are, what did I say, 12? What's 12 times 4? 48. So the size of this memory address is 48 bits. That's how big that number is. It's a 48-bit memory address. So how much memory is addressable then? Let's just let's geek out a little bit on this. So if I have a 48-bit memory address, how many unique buckets of memory do I have? To the 48th power. I have 2 to the 48th power of unique memory addresses that I can create. And that's, do I know how to read that number? That's thousands, millions, billions, trillion, 281 trillion, 474 billion, 976 million, 710,656. It's a lot, but it's not infinite. But I'm telling you that under the hood there, this is probably a 64-bit operating system. So if it's 48 bits, I'm missing 16 bits of memory. Where do you think that other 16 bits is being used for? Yeah, operating system reserved 12 bits of addressable memory that's only allowed by the operating system. So it held back. What it did is modern operating systems kind of create protected memory versus user memory. So this is more of an operating system, systems programming kind of concept. So you'll deal with this more in the 450 class. But you have 16 bits of addressable space that's reserved only for the operating system. Your user programs can't access it. It's a whole different ball game. Versus 48 bits of user addressable stuff. What does that mean? It means you can't write a C++ program that crashes your operating system, because you can't walk into protected memory. Okay, you can bash around other programs and stuff all you want. You want to rip Microsoft Word apart or something. Although now a lot of times they're stored inside of I don't know, maybe call them micro machines, kind of a virtual machine, but built on top of hardware to protect them from each other. So that programmers don't necessarily go and overwrite memory of another user program running on the system, but at the very least, we're protecting the stability of the operating system that says, hey, you can't just walk into OS space and do stuff. When you do the 450 class, the systems programming class, there are tools. We have these things called system calls, which you've historically seen. Remember when we looked at the Hello World program in Linux? And we said, hey, yeah, this looks scary, but it's actually leveraging power tools. Like we had syswrite and stuff. Syswrite, for example, is something that the operating system, it's a program that the operating system runs in its protected space. So we can't use normal syntax stuff to get to it. There's special libraries that allow us to jump from user memory space to protected memory space, but it governs that process to protect us from ourselves. We can't just haphazardly, accidentally walk off the end of our array. We have an array that has 5 buckets. We try to access bucket 19, and now all of a sudden we're running in the neighbor's yard, right? And it just so happens that neighbor is part of the operating system, and now you got to reboot your whole computer. You roll back to when I first started learning C and C++, you take a wrong turn with your program, the fix might be restart the computer because you just crashed your OS because it didn't have protected memory. All right. Oh, easily. That's why C and C++ were kind of nightmare languages early on. I know you guys are having a blast with it. I like using it because it does scream at you plenty. It gives you that reinforced learning, right? Like parochial school type stuff. What's up? Yeah, you're forced to do it. Where before, I mean, because one of the things is beginning programmers, you make a lot of mistakes. I mean, it's the nature of learning programming. You spend more time fixing your mistakes than you spend writing the right stuff. In the end, the right stuff is 7 lines of code, but you spent 4 hours to get those 7 lines of code because you had a zillion errors and stuff. Well, imagine if you had computer reboots in the middle, right? And you go even older than that. So those you were in the, you're all taking the 175 class right now, right? Have you talked about punch cards? Okay. So go even older than that. Now you got these physical stacks of paper that you've punched holes in. You take it up to the batch processor and say, okay, here's my program. Go ahead and run this through. You go and sit down and you find out, oh, I got a bug. Back to the seat. How did we ever get to where we are today?
Patience.
I mean,
Dedication.
one thing that I want you to take from the last 5 minutes is this is kind of a gold conversation, if I do say so myself. It's we're actually exploring the history of computing. Everybody knows who Bill Gates is? Okay, who's Bill Gates? Microsoft dude? All right. What gave him the advantage to create something like Microsoft? Why did we have such a jump in technology kind of during Bill Gates, let's call it high school age? Anybody know?
Why do you think that we're more-
Okay. Maybe was it the transition from punch cards to programmable computers? So that was when the transition happened, and computers were really, really, really expensive. Bill Gates went to a private school, and one of the, I don't think it was one of the parents of the kids, but a friend of them owned some big fancy computing company. And, you know, the owners of these companies didn't know that much about the computers. They put a fancy schmancy, nobody could afford, no normal people could afford these computers into the school, and had the geeky kids go and play with it. Bill Gates and his couple of buddies. So they sat there and they started writing software on the first non-punch card based thing where you can fix your bugs instantaneously and run it again.
Because they get to explain
You wish it was 20 grand. It was way more than that. But I mean, what we're seeing there, and if you were interested in this stuff, just in the last second, there's a author, Malcolm Gladwell, and he has several different books, but one of them that you might look at is a book called Outliers that talks about this kind of stuff. You know, if you look at the richest people on the planet today, yeah, they're smart people. They made some good decisions, but they also grew up during a period of time where there was an important transition that they were right there, so they had an advantage. Like one of the things in there, and you can pack up because the class is over, but one of the things they had in there dealt with like the NHL, professional hockey. Like the starting fact was something along the lines of 75% of NHL players are from Canada, something like that.
You can practice.
That's not it. Okay. No, actually, I'm sorry. 75% are from Canada. Of those from Canada, 80% of them have birthdays in the first 3 months of the year. Why? You know, so that some of the guesses are, oh, maybe the parents were celebrating the Stanley Cup or something like that. It has to do with the cutoff age for junior hockey. If you were one of the older kids in your league, you tended, especially younger kids, they're developing and they have better hand-eye coordination as they get older more quickly. They were getting better coaching. They were getting more ice time because they were the older kids in the leagues. They became NHL players because they had those advantages, just because of their birthday. Yeah, so Outliers is kind of about that stuff. It goes through a bunch of scenarios like that you're like, it makes sense when you hear it. There's another cool one has to do with you take 10 15-year-old Chinese math students and 10 15-year-old American Chinese or American math students, and you say, hey, you have to memorize 5 numbers in 30 seconds. 100% of the Chinese students can do it. 20% of the Americans can do it. Why? Yeah, so our go-to move is, oh, you know, the Chinese students, they're just better at math, right? That's our stereotypical crap. It has to do with the efficiency of the Chinese language. Our human brain's on about a 2-second loop, and the Chinese language will allow them to say 5, maybe it was 7 numbers, but can say that many numbers in less than 2 seconds.
That's scary.
Where English is less efficient for expressing those values. So that whole book is about stuff like that. It really changes your perspective on things, throws a lot of stereotypes out the window, but makes you realize how stereotypical we are. Because that's where your brain originally goes, right? You know, like, oh, well, Chinese guys are just better math. That's where we go. All right, I'll see everybody on Thursday.
So, Thursday?
Yep.